Hello, everyone. My name is Ibrahim Hassan, and I'm going to talk about CFD for for tall structure buildings. Uh, my background is I'm a civil engineer. I'm a PhD student currently enrolled at Cairo University with Professor Yusuf Rashid. And I've been working with CFD since my master's degree. I've worked with CFD for natural ventilation, and then I've been working with many consultants to use CFD for tunnel ventilation and for the conference halls ventilation and smoke extract in case of fire. But today's topic is currently different because it's how to use CFD for high-rise structures. And we're going to talk about how can we predict the pressure distribution across the height of the building, especially when it's tall structure where the wind force and wind pressure currently achieves very high values as when we go up at higher elevations. Why we should care about simulation, how can we help us, what's CFD, what are the steps that we use to achieve results. We're going to talk about a case study, and then we're going to talk about an important phenomenon, which is the vortex-induced vibration, where due to the wind load, some vortices are accumulated or some vortices are took place at the leeward side of the building, and we're going to talk about it. Then we're going to make some summary for our presentation. In fact, tall buildings are very crucial in the modern urban environment due to their efficient land use, and they promote economic growth, and actually they are a very good investment and they attract investments. However, for structural engineers, significant wind loads would be a problem, and accurate prediction of these wind parameters upon these structures ensures a safe and optimized structural design. Actually, CFD helps to simulate the wind and how it interacts with the building, including the pressure distribution on the building surface. And traditionally, wind tunnels are used to measure the wind effect, and this is how most of the codes are based on empirical formulas based on tunnel tests for different setups. However, CFD can be a very cost-effective alternative. We cannot depend only on CFD. However, we need the experimental testing of the wind tunnels. But in fact, CFD can be a very cost alternative, can help us reduce the cost by reducing the number of tests of the wind tunnels, and it can help us simulate very complex scenarios, especially in places like coastal areas where wind velocities can be variant and can be very high. CFD simulation is a very cost-effective way to simulate the wind flow and predict pressure distribution across the surfaces of the building. Our industry has many, the design process is very complicated and should be on time and should be on budget, and it has so many uncertainties. So CFD helps us to cover some of these uncertainties and provide us with more information that can lower the cost and keep deadlines, and in fact help prevent failure risks for tall buildings. CFD is a science of predicting the flow, and it's a very powerful engineering tool. We can predict the flow of any fluid, so we can use it for airflow or fluids like mechanical engineers can use it for the oils or the engines or whatever applications they have. It can also be used for heat and mass transfer, chemical reactions, and any related formula. CFD solves the equations for conservation of mass and the Newton's second law, in which we use the Navier-Stokes equation, which represents the conservation of momentum. And if we include the temperature, so we're talking about conservation of energy and enthalpy, and any other quantities that is transported, for example, pollutants, or if we talk about species like fire or carbon monoxide or whatever. CFD analysis complements testing and the experimentation, and it's very effective to test so many scenarios. The CFD solvers are based on the finite volume method, in which the domain or the volume of the fluid is discretized into a finite set of control volume, and each control volumes has the general transport equations, which are mentioned here below. This is a general transport equation, taking into account the if we change the parameters phi, we get the continuity equation, and if we change it for the velocity in x, y, and z, we get the momentum equation by Navier-Stokes equation. And if we change phi in the equation with in enthalpy, we get the energy equation and the conservation of energy. So these are partial differential equations that are discretized into a system of algebraic equation. All algebraic equations are then solved numerically to render the solution. And since our flow might be turbulent, these fluctuations and randomness and chaotic behavior makes a direct solution for the classical Navier-Stokes equation very difficult. So as there are different methods to represent the turbulence, and the most common and widely used method is the Reynolds average Navier-Stokes RANS system, in which we use additional terms like the K-epsilon model. The model used two transport equations to model the turbulent kinetic energy and its dissipation rate. If we're going to solve a problem using the CFD, we have to be aware of what is our goal and where are we heading. So we have to define the problem clearly. Then we have to model our geometry. And we mean by this modeling the domain of the fluid in which the fluid will flow. And then we provide the loading criteria and the boundary conditions. Then we discretize our domain into smaller control volumes, prepare our problem setup, test our conversions, and then post-process the results. Our objective in our case study, we're going to talk about our case study right now. We have two towers in Maadi area in Cairo, and their height is 150 meters. And we are here to evaluate the wind-induced pressure distribution across these two towers and have an insight on the aerodynamic behavior. First, if we talk about the geometry, model has been prepared using AutoCAD 3D and then have been imported into ANSYS Fluent and been prepared with space claim geometric application, in which we have defined the domain of the fluid flow, and this domain should be should be big enough to capture the phenomena, to capture the flow and capture the phenomena behind the buildings. And in order to define the wind load, we have used data from the Egyptian Meteorological Institution, in which we have studied the wind velocities in this area for 30 years. And we found that the velocity ranges around 15.5 meters per second at the elevation of 10 meters. However, our building is 150 meters, so using a logarithmic scale, we can predict the velocity and the wind profile above the ground till 150 meters. And we used another model to predict the wind speed for the next 100 years based on the data available, and we predicted that it might reach 20 or 23 meters per second, and that's another scenario. We have another wind profile for a higher wind speeds for a prediction in 100 years time. And lastly, we have also the wind values assumed by the Egyptian Code of Practice, which is 33 meters per second constant along the height of the building. The third step is to create the mesh and the discretization of the domain into a control volume, and we have to be very sure and very accurate at the area surrounding the building in order to capture the gradients and the differentiation in the velocity and pressure. And we go bigger slowly till we reach a higher volume across the domain. After testing the meshing, we have to make sure that our mesh, that the data and the results does not change with the mesh size. So we have to test so many meshes, a coarser mesh and a finer mesh, and the results as this graph shows that they go well together. And in fact, we use the finer meshing because it's it will be very accurate in capturing the phenomena we are checking, which is the velocity and the pressure in this situation across the building. Our boundary conditions are velocity inlet boundary condition with the profile mentioned before, pressure outlets, and we use the walls and symmetry boundary conditions for the left and right hand sides. We use the turbulence on the K-Epsilon turbulence model, enhanced wall treatment. Our case was a steady state case, number of iteration is 600, and we used a coupled solver scheme for the pressure and density, and the convergence criteria based on two main issues, which is residuals to be a very low number, 10 to the power -5, residuals representing the numerical errors, and the mass flow rate between the input and output shall be 0. Here are the results for the scaled residuals, which is almost stable and in a very low values. It started with the larger values and then went down with the low values. Same for the mass flow rates between the inlet and the output. It's almost 0, which means we have achieved convergence. Then we're going to go with the post-processing and the results. But before we talk about it, we have tested so many cases because CFD allows us to make different setups. So we have defined 6 cases. Case number 1 is based on the Egyptian Code of Practice, wind velocity 33 meters per second and constant along the height of the building. And case number 2 is a logarithmic scale, 23.6 meters per second at 10 meter height. These case 1 and case 2 for the north direction, and case 3 and case 4 for the northwest direction, 30 degrees left from the north orientation, and case 5 and 6, which is another orientation, is the southwest orientations. And these are the 3 main orientations in which the wind is prevailing in the Maadi area based on the data from the meteorological data. We're going to go through the results. If we watch the velocity for one of the cases, we're going to see that the buildings surrounding affect the flow of the wind, and as a result affect the pressure on the surfaces of our tower. This is the A03 tower, and here is the A05 tower, and it looks very well that there are so much venturi effect due to the buildings surrounding and achieving a very high pressure on the northern surface of the A03 tower. That's a section presenting how the velocity looks like on the A03 tower at the top and the A05 tower at the bottom. Here are another section showing the 2 towers together and the air flow rate is coming from the north side from here, and how the surrounding affects the wind pressure on our buildings of interest. Here is the pressure results, plan view showing that the A03 tower has a higher pressure values than the A05 tower. Here is a vertical section showing the pressure along the height of the building of the A03, and here at the bottom for the A05 tower. And here is a cumulative section showing the A03 and the A05. It shows the A03 has a high pressure from bottom to up. However, the A05 has a high pressure at the top areas. Now you can find the you can find the pressure values for the A03 tower, the north side at the top and south side at the bottom. The north-south shows a windward side with a positive pressure of nearly crossing the 1000 Pascal. However, for the south side is a leeward side showing a negative pressure around negative 500. If you watch the A05 tower, you're going to see that the pressure is very high at the top of the tower with values reaching 1000 Pascal. And at the leeward side, it shows a high to suction and negative pressure values of almost negative 400, 500 pascals. The results has been compared with the Egyptian Code of Practice pressure values for the design, and actually for the windward side, it shows a very good agreement, and in the leeward side, the Egyptian Code of Practice has been more conservative. And the results show that for the A03 tower, the north facade shows the highest value of 1195 Pascal for case 2, and south facade negative 503 for case 2, east facade 1220 for case 6, and west facade negative suction 672 for case 6. However, for A05, the values are lower than the A03 tower. So A03 tower is a critical one to take into account. And the last phenomenon we're going to talk about is the vortex-induced vibration, which refers to oscillations in the structures caused due to the periodic shedding of vortices that are formed behind the building. If we look at the picture at the right, we found our building in the orange color. When the wind is coming from the left side and it reaches the edges of the building, vortices are formed, and then these vortices are getting bigger. Actually, in this area, they are making a low pressure areas at the left and right of the tower, which in fact can be translated into forces and make a crosswind response force. And if the oscillations of these vortices has achieved a natural frequency which is very close to the natural frequency of the structure, these crosswind response force might cause a very high fluctuations and may achieve peak. So in some types of winds, in some values of the wind velocities, the response might be really very high due to the matching between the frequency of the vortices and the natural frequency of the building. And in our case study, we have used a workflow in order to see how the vortex-induced vibration can be studied. And we had so many input parameters for our structure. Then we used it to calculate the Reynolds number and the Stroud number and the shedding frequency. And then we calculate the natural frequency of the building. After calculating the natural frequency, we can calculate the reduced velocity. If the reduced velocity is lower than 4, so there is no need to further simulation, and no buffeting or fluttering could occur. Fluttering is higher oscillations for the building can take place, and same for the buffeting, but buffeting is due to the fluctuations of the vortices. If the values of the reduced velocity is between 4 and 8, we have to check the lock-in, and we have to check if the frequency of the vortices is near to the natural frequency of the building, and in that case gonna make a crosswind force which gonna be achieve oscillations for the building might be very high and might cause fatigue. If not, we won't be necessary to make any other studies. However, if the reduced velocity is greater than 10, we should perform a buffeting and fluttering analysis and make sure that our design is safe, and we have to check serviceability. And we would like to finish the presentation with some ideas about how to improve the design and how to reduce the effect of the vortex-induced vibrations. So instead of using a constant cross-section along the tower, you can use a tapering cross-section in which the top of the building getting smaller as we go high. Another issue is you can make openings in the building like the tower in Riyadh. We can make cross-section changes along the tower, like what's happening in Burj Dubai. And another very simple strategy is a softened corners, which helps reduce the vortices. And we can use one or two or three combination of these strategies. If we talk about the vortex-induced vibration corner softening, we can see from here that the sharp edge has a very high amplitude for the vortices. However, for a very simple structure like softening the corners and making it not very sharp, shows that a very lower amplitude. If we translate this into graph between the time and the pressure force on the building, we find the red one is the sharp corner, shows a very high values and intermittent values. However, the blue one shows a very periodic and low pressure force values, which would be very favorable for the structure engineer to work on. And to sum up what we have been talking about, CFD can be a very helpful tool, can provide a very detailed pressure distribution, ability to simulate different wind directions, can provide transient and time varying wind forces, can be integrated with the finite element. However, it is very computationally costly, and sometimes may be very complicated, and accuracy of the turbulence modeling can be challenging, and should be some validation with experimental and wind tunneling data. Hope we have given a brief on the CFD and how to use it to present the pressure distribution on tall structures, and how the vortex-induced vibration can make fatigue and can provide failure. So need to take it into consideration while designing our structures. Thank you, and looking for your questions.